In this video, we will get acquainted with a very clever way of illustrating fundamental processes. Quantum field theory is very complicated as shown in the introduction video. Therefore, many people might feel uncomfortable with quantum field theory since the math is really complicated and requires many years of study to fully tackle. While you really do need to learn this complicated math to work with quantum field theory professionally, you can actually understand the most essential physics without any of this math. This is possible due to the famous Feynman diagrams, which were introduced by the American physicist Richard Feynman in 1948. Using these diagrams, we can discuss and understand fundamental processes in a much simplified way, using diagrams instead of math. In this video, we will go into details on how to use and understand such diagrams. Quantum field theory is used to describe the world at the most fundamental level. This means the level at which particles like quarks and leptons interact via different forces. This could, for example, be how two electrons repel each other via the electromagnetic force. Such processes are rather complicated mathematically, but Feynman diagrams let us consider such processes in a pictorial representation. This makes it much easier to understand whatever process we are interested in. The probability amplitude of a process, like the repulsion of two electrons, contains several variables and integrals, but using a handful of Feynman diagrams, we can understand these processes intuitively. If we want to calculate the result of a given process, we then have to actually calculate all the ugly math, and this takes practice and sometimes computer tools are used. But in this video, we will just learn how to draw the diagrams correctly using a simple toy model and show how the math works in the simple model. The concept is the same for real physical theories, but in such theories the math is much worse. Thus, considering a toy model, we can understand the essential steps and concepts without needing advanced mathematics. The Feynman rules are different for different forces and models, so we will start with one of the simplest toy models we can think of. Let's consider spin zero fields, thus scalar fields, which means we only have numbers, no vectors or matrices to make things complicated. Let's say we have three particles, thus three scalar fields, and each particle has some mass. Let us call these masses MA, MB and MC. To make particles interact, we need a vertex. Thus, our toy theory will have an interaction vertex where the three particles interact. The simplest process we could come up with would therefore be the decay of the heaviest particle into the two lighter particles. Now, when drawing any process, we must firstly make sure that the process is kinematically allowed. This is to make sure that we do not violate conservation of energy. Thus, if we say that particle A is the heaviest, then the combined mass of particle B and C must be the same or less than the mass of particle A. This gives the following relation. M is larger or equal to the product of MB plus MC. If the mass of C and B combined is less than the mass of A, then the excess mass will turn into kinetic energy of the B and C particles. Thus, they will move faster than A. If this condition is satisfied, we can have the simple decay process where particle A decays into particle C and B. Note that we use the convention where time runs from left to right. With this simple toy model, we can do more than just the simple decay. If we combine two vertices, we can create a scattering process, where, for example, two A particles interact via the C particle and turn into two B particles. In this process, the C particle is like a mediator of the interaction between the incoming A particles, and this process is a bit like the weak force, where the C particle mediator force changes the A particles into B particles. Notice that because we have two incoming particles, there are different kinematical constraints. We can also have the reverse process where two B particles turn into two A particles, even though the A particle is heavier. To satisfy the kinematics of this process, the two B particles must have enough kinetic energy to compensate for the mass difference. The kinetic energy then turns into the mass of the A particle, at least partially. This would mean that the outgoing A particles would move slower than the incoming B particles. We could also think of many other scattering diagrams by combining two vertices in different ways. We can also consider the two diagrams of an A particle interacting with a B particle via the C particle mediator. This would lead to two diagrams, where the first also resembles a weak force interaction where the particle changes type. The second diagram looks like a general annihilation diagram where matter and antimatter particle annihilate and then reform. We could make a couple of other combinations of just the two vertices, but it should be clear that we have already managed to make a lot of different diagrams for different processes. These diagrams are just simple Feynman diagrams for simple processes. We can also have three vertices, and then we can make so-called loop diagrams to the decay process where particle A decays into particle B and C. Loop corrections are generally very complicated for physical theories, and therefore we will not go too much into it. But these loop diagrams give us corrections to the process without loops called the tree-level diagrams. Depending on what you are looking at, these loop corrections can be important. We could also consider what diagrams we could make with 4 vertices and 5 vertices and so on. You can actually make an infinite number of more and more complicated Feynman diagrams. Therefore, it is important to understand the ordering of a process, because how do we know what diagrams are important, and how can we get useful results if we have to compute an infinite amount of Feynman diagrams, which is impossible. Luckily, we don't have to compute an infinite amount of Feynman diagrams. Every vertex contains a coupling constant of the theory you consider. We often call the coupling constant G, and this constant is simply dimensionless, and it generally has a value between 0 and 1. This is very important because this means that higher order diagrams are less important. This is because every vertex gives a factor of G. Thus, if you have a simple decay process, you just have G. But loop corrections to this diagram has 3 vertices, thus you have G cubed. Let's say that for our toy model G is equal to 0.6. That means that our tree-level diagram of the decay process has a coupling factor of 0.6. Now our loop diagram to this process is less important, since we have G cubed, which gives a coupling factor of 0.216. Thus we can roughly expect the tree-level diagrams to be roughly 3 times more important than the loop diagrams. There are of course other factors, but this is generally how it works. Likewise, the diagram with 2 loop corrections will be of order G to the 5th, giving a coupling factor of less than 0.1. Thus we can see that the higher order diagrams quickly become insignificant. This is important because in principle there is an infinite amount of higher order diagrams with more and more loops. But they are increasingly unimportant, and in some cases you can get a sufficiently precise result just by calculating the tree-level diagrams. It should be clear how it works with the ordering of the diagrams now, and that for this to work the coupling constant must be between 0 and 1. Now let us discuss how to build Feynman diagrams and how the math would work for our simple toy model. As discussed before in this model, we have just one vertex where our particle A, B and C intersect or interact. All the different processes of the model are then based on the different ways we can put these vertices together such that the diagram is kinematically allowed. Because we have a scalar field, we don't have to worry about the math of the incoming and the outgoing particle. What we should do is label the incoming and outgoing particles to make sure we don't make mistakes with the math. To keep it simple, let us say that the vertex factor is equal to minus Ig, and then the propagator or mediator will give a factor of I divided by Q squared minus M squared. In the end, you multiply with I. With these simple Feynman rules, we can now draw any diagram of this theory and with relatively ease figure out the probability amplitude of this process. This amplitude is part of what you would need to compute to calculate a result that you can test in an experiment. If we use these rules, we can easily compute the decay diagram. We can label the incoming A particle as P1 and the outgoing particles B and C as P2 and P3. In this process there is no propagator, thus the only mass we have to collect is the factor of minus Ig from the vertex. The amplitude is therefore just m is equal to g after multiplying with I. We can also compute annihilation diagrams of particle A and B with the C particle propagator. Again, we can label the incoming and outgoing particles with P1, P2, P3 and P4. The propagator we now label with Q. We now have to collect two vertex factors in accordance with the Feynman rules. Putting all this together gives us the following amplitude. M is equal to g squared divided by q squared minus m squared, after multiplying with I and cancelling out minus signs. The q is the momentum of the propagator, which can be expressed in terms of the incoming particles as q is equal to p1 plus p2. We have thus found some amplitudes for two different processes using Feynman diagrams and rules. We could discuss more diagrams and processes, but then the video will be very long. I hope Feynman diagrams and rules make more sense now, and it is hopefully clear now how they can pictorially help us understand processes, and the Feynman rules let us convert the diagrams into math that we can compute to get real results. Of course, we only looked at a scalar toy model, but the concepts are completely the same for any other model. The main difference is the math. We will look more into Feynman diagrams when we will apply them to real theories to discuss particle physics. And we will also need them in our discussion of fundamental forces and all the different processes in the standard model. If you have questions or suggestions, put them in the comment section. As always, I hope you learned something new. If you did, please like and subscribe. You can also buy me a coffee in the link below to support the channel. I hope to see you in the next video, so stay tuned.